let me start by speaking about product lifecycle design. As I told you, this is an introduction. So I'm going to talk to you about product environmental effects and requirements. As we have, when designing product, we have different types of requirements. We have normative requirements, we have ergonomic requirements, and so on, functional requirements, aesthetic and cultural, and so on. Just one slide about lifecycle assessment. That would be an entire course. And then lifecycle design approach, especially the lifecycle concept and the functional approach or functional concept. A few things about the product lifecycle design criteria, which are material designed for material minimization, designed for energy minimization, designed for non-toxic resource selection, and designed for renewable and biocompatible resource selection, designed for product life optimization. We will see later what does it mean. Designed for material life extension, and designed for disassembly. Okay, that's it in a very short time. Product life cycle design. It's actually most common to other terminology like eco design or design for environment or design for other things and so on. But I rather prefer life cycle design because it's actually in its wording saying something about the approach that we have to have the life cycle. And I told you something in the last lecture very briefly, so something should be there already in your mind, but we'll see that. And nevertheless, this is the discipline that since the 90s start to integrate the environmental requirement into the design process together with the other requirement, as I said before. And are the environmental requirements from? They are coming from the environmental effect or the environmental impact. So it's this is what it's saying. And we said something in the other lecture about the environmental impact that could be related to a product, but anyhow the environmental effect or impact are linked to any exchange of substances that may occur between any process that is related to a product, and we will see how we have to relate this to the product between the industrial system, the production and consumption system, and the nature, the geosphere and the biosphere. And we may have, of course, input, so when we take resources from nature, and output when we have emission. Going there to the, and of course, not everything have in terms of either input or output the same impact. If I'm throwing 1 kilogram of water into the environment, it's different from throwing 1 kilogram of asbestos into the environment. One is very cancerogenic, the other one maybe not that much. All right, so it's a matter of quantity on one side and quality on the other side. When we speak about input, there are two key issues. One is related to resource extraction, and when we speak about resource extraction, this is mainly linked to the fact that we have to guarantee to the future generation some resources for them to go on, to sustain their life. We have to guarantee resources for the new generation. We remember the definition of sustainable development. I believe that we talked a while the other time. But there is another fact that is more environmentally linked, that during the extraction processes we may have some environmental impact. When we, for example, to have oil that maybe is used to produce the plastic that we have, for this lacquer here, during the process of extraction, fertilization of oil, there could be damage to the environment. Okay, and then the output. I don't go through those. We saw them very briefly the other time, and this is not the course to speak about this. But basically, we are speaking about global warming, ozone layer depletion, eutrophication, acidification, small toxicity, waste, and then there are other like noise, electromagnetic impact, or radioactive, or land use, and something like this. But the point here is that these could be linked somehow to a product, to the microphone I'm using, to the chair you're sitting on, or to the beamer that you're using for the lecture here. And in fact, the real point and the answer came during the 90s was, but can we really associate those big impact, like global warming, a quantity of global warming, to the microphone that I'm using, to the webcam that is video recording me here? Is that possible? Or, other things. And how to do that? Well, the answer actually is yes. And there are two key approaches of doing this: to consider the life cycle of a product, and to consider the functional limits. And there is an evaluation method to do this, which is called life cycle assessment of product. It is related to product. I told you even then that was a methodology, and then several tools were developed, and they are still under development. So we find those in different ways, but it's the most trustable tool. It is standardized ISO 14 and several 14666, several ISO standard saying how to do that. And we are using, for example, as we said, even in the other course I teach how to use FCA in a course on how to design a product. We are making consultancies with companies using life cycle assessment, the design process, and so on. And so which are the approaches? The first one is actually to extend the design horizon from just designing product, as we are usually, or you as designer are usually thinking to design it, to designing the product life cycle stages, or to design the stages of product life cycle. And which are those stages? Are the pre-production, the production, distribution, use, and disposing, or the end of life. And the pre-production, what is the pre-production? Before the production is basically the production of material or energy. So we have extraction processes, and then processes to produce the material or the energy that is available for the real production process, which you can go in a very simplified way. This is very schematic, right? But manufacturing processes to transform material into components, and then assembling, finishing processes, and so on. Then into distribution, we have the packaging. To have this product here, I need a packaging. And so in a life cycle design approach, and in a life cycle assessment, I have to consider even packaging that is used for this product here. All right, and transportation and storage. Storage for in some cases there is very little to say, but for some product, for example, you have maybe to keep them in a refrigerator, so you are consuming lots of energy to keep them. It could be that the storage is the most impacting phase of a given product. You never know. This is something important we will learn. And then there is the use phase. For this table, maybe nothing is happening. For the computer, I'm using energy. And as we said the other time, it's not that the energy I'm using here is impacting in that moment. When I'm producing the energy, it depends what kind of energy and which sources I'm using to produce the energy. But there I'm making some impact. But as well, it could be at the end of the life, right? If this computer to have the energy actually has even some battery here inside, and this has to be disposed of. So we may have some problem. We will definitely have some problem in disposing this battery because they have heavy metal inside and stuff like that. Okay, so use, and then we have disposing or end of life, in which a different path could happen. So we may have that the product goes to landfill, which is basically the worst. We are not giving any value to that, or we can make incineration with burn, or we can compost. It depends if the product is a product that could be composted, or we can recycle this, or we can actually reuse some part, and so take this part by simply reusing them before the use phase. Okay, so I can reuse this computer for a second market or give it to someone else, or some processes are needed before actually reusing this computer. This has to be remanufactured. It has to go back to the factory because some components need to be refabricated for some parts need to be substituted, or and so on. And before that, there is always a collection. And this collection actually could end up in the same life cycle. So for the same product, that means all is going to reproduce the computer for the same company producing computer, or it may go to other product life cycle. So I can recycle material for the same computer, or to make other things, a bottle, or I don't know, something else. Okay, so this is important to understand and to think the product in terms of its life cycle. And actually, I have to add, in relation to all the inputs and the outputs of all the processes that are part of all the life cycle phases of the product. Because, as I said before, those input and output, it determines global warming, eutrophization, acidification, and so on. Okay? So I have to know which are all the processes of all the product life cycle stages, and then I have to understand which are the input and output of all those processes related to this microphone, this cup of coffee, or whatever, the mobile phone you have in your pocket, and so on. And the other thing you remember, we talk about the functional unit or functional approach. This is key important really, in functional, in a life cycle design approach. And you remember I show you some example of product. For those that were not present, this was an example of a pen which is made with a biodegradable material, cornstarch. And okay, you can say it's biodegradable, but then compared to a Mont Blanc pen, that is that product will last nothing compared to the other one. Okay, so it could be that the single product, the biodegradable pen, is good, but if you compare in relation to the function to have a pen for a given period of time, 20 years, 1 year or whatever, maybe you need one Mont Blanc, but you need several of the others. So you have to compare one with the several of the other in their life cycle. So, as we said the other time, it's so that maybe the single in its life cycle, as the first principle I just mentioned, it could be that the environmental impact is lower, for the other pen is higher, but in terms of the function in time, the one that is lower, because we have to reproduce, produce, distribute, and dispose many, it goes up. And so the impact of the other is definitely higher. So we show that as one of the worst example of product with a low environmental impact. Not to say that biodegradable material are bad. It depends on which product you are using them. And we will see something about that today, even the short. So defining the functional unit is really important. So you have to say, for example, in this case, we have to think in terms of the function. Function is to have a pen that works for a given period of time for a given task for a student that is taking notes at the university or somewhere else, or okay. So that is key and key important. And a functional approach for the designer, it was a big debate between function and form in the course of history of design. Function has been revisited in relation to sustainability, but taken this perspective, which is very, very important. If we forget this, we make so many mistakes, and so many mistakes has been made, right? It's fundamental. And then, of course, there is the last approach is the environmental design, that we have to have an environmental design objective. So we have to set these, we have to adopt the life cycle and the functional approach. We have to minimize the overall impact of the input and output of all the processes of all the life cycle stages of the product. Okay? And then you say, wow, but is it really possible to make, to assess for a given product, again, for the microphone, the computer here, this cap, and airplane, the mirror, or other things, the environmental impact of that using those criteria? Yes, it is, and we are using life cycle assessment. There are even other tools, but this is really the one that is most transferable, is most used, and it's better to use actually. And here, I don't know if I made you the other time the example of 2 life cycle assessment. No, for the present, no. So I thought to just to make some understand what is your perception about that. Here I made a life cycle assessment of an upholstered seat like this one, with an upholster over, which is an estimated 8 years lifespan. We have to define this because this is related to the functional unit. And can you guess? This is the life cycle assessment. I didn't. You will see later. You will see where is the highest environmental impact. But can you guess in which of the phases, in the pre-production and production, I put that together, in distribution, use or disposal, where you think is the highest impact? In disposal? And what about the other? Pre-production and production. Distribution. And others. Can you think about it? Why? Well, yes, someone was true, but you can see that distribution and disposal, they are really low compared to the other. Many times we really think that disposal is the biggest impact, and distribution, it is. And well, it depends on product. This is the profile of this product. You will see another one. It can change. And for example, you see there is an impact in the use phase of the chair. Can you guess why there is an impact in the use phase? Someone has to wash it. Okay, so using some detergent and some other. And this, considering the detergent they use and whatever, is impacting more than. But this is telling, for a designer, is telling a lot. For example, it's not to say that we don't have to consider disposal and distribution, but for sure, the pre-production and production, which is related to the fact that we have to reduce the environmental impact of that, but considering the life cycle, maybe it's good to extend the life of that product because that phase will be decreased because it's, that impact, it will be distributed, along the year compared to the other phase that remain fixed. But then that maybe we have to consider even the use phase. So how to design these to be easily washed and maybe without detergent that has high impact. Okay, just water washing or other things. Here put another one. The washing machine, 10 years lifespan. This is optimistic actually. Nowadays the washing machine doesn't last that much. To use this tool is very important because maybe we don't know how much really one phase is more important than the other in terms of impact. So where is there is a priority of intervention when we have to redesign the file. Okay, so to understand the profile before starting to design is key important. Well, of course, and in the course we are using life cycle assessment on an existing product. We have a tool to define priority, and then we have other tools to follow the design. This is not what's going to be lectured here, but for your knowledge, if you want to study this, I think it's as well important as system design for sustainability. So when we speak about product lifecycle design, it's quite easy to say, but is this design of the product lifecycle stages that while considering all the other requirements, aim at minimizing the environmental impact of the product, considering the whole life cycle phases and the functional unit. So it's clear. So when we as designer, we have to think in functional terms in designing the whole life cycle phases. And which are the criteria that has been developed. Here you will see some that we are adopting here, but they are quite similar to other developed by other colleagues, researcher and professor in Europe and worldwide. To design for material use minimization, to design for energy use minimization, to design for resource conservation and renewability selection, for resource non-toxicity and harmfulness selection, for product life optimization, which means to design for extending the life of the product or using in a more intensive way, material life extension, design for recycling, energy recovery and composting, HC, and design for disassembly. Actually, there is no time to say, but when you design product life optimization and material life extension, you go back to the other 4 criteria in a sense, because if you design for extending the product life, you are producing less because you need less production. If you design a product that lasts for 10 years, we will see that later a bit better with the scheme. It means compared to another one that lasts 1 year, you have 10 and 1, you have to 1/9 of pre-production, production, and distribution phase, and so on. Sorry to go on. And design for disassembly, it is functional to product life optimization and material life extension. And very briefly, we will see this. So if we see design for material use minimization, we have to consider all life cycle phases again in the functional unit. And here I cannot go into any detail, but there are guidelines, there are examples, and there are very many things. And here is the theory could be very large. I'll just give you some few very simple examples. This is an IKEA sofa, which is made of polyethylene cells, which are use a hair dryer to fill them. And of course, compared to a traditional sofa, you can guess that they are using air instead of lots of material. So basically, the use of material is 10% compared to other materials. I'm not speaking about the quality of the material. Design for energy use minimization. Again, we have to consider all the life cycle phases in relation to the functional unit. This is a refrigerator by Ursula Fischer, a very good friend of mine, one of the best researchers and designers for designer working on design for sustainability worldwide from Germany, from Cologne. And she made a while ago this refrigerator. Actually, you can see one very easy thing in front. There are several doors. It means that you don't, if you need something from one part of you just open that. You don't open the old door, letting all the cold that is inside to come out. So it's better to fragment this. But the other thing is that she designed this as a refrigerator that is embedded in a specific part of some typical houses in Germany. There is someone from Germany who can say if this is true or not, that there are some parts that are much near the outside of the outside of the house. So it's like to put the back of the refrigerator almost outside. So taking in the cold season, the cold from outside without the need of energy to cool the system inside. So for 5 months a year, there is no need of electricity to cool the system because it's actually taking the cold that is coming from outside. Design for resource toxicity and minimization, again, life cycle. And this could be when you speak about resources, about material and energy, of course. And so this is a very easy example. These are racks made of microfiber. Now they are quite common, but because of the microfiber, how they are made, they can capture some dust and other things without the need of detergent in many cases. So you are not using detergent, it may be toxic both in production and actually while in use and in the disposal, because then you put the flacons to the bin and then maybe to be recycled as plastic, but there is always a residual of this detergent there inside. And design for resource conservation and renewability, again, could be in terms of material and energy. And there are several examples, but just to give you an idea, this is a shuttle that has some solar panel on the roof, so that it's just moving with the electricity that is delivered by the solar panel into the electric engine that is then moving the shuttle. And then material. So we made some better example of biodegradable material and renewable material. Many times biodegradable and renewable are the same. So when a material is renewable, it could be biodegradable. This is the case of Matter V, which is produced by Navalon. And in some cases, this doesn't work, as we saw before. But if we use this for a bag for organic waste, that's the best. You just take this and then you throw, and it will become waste, so you don't have to take it out, and that's very good. But even I put another example, not just to have that vase, a vase for flour. So you put the vase into the ground, so you put it together with the vase, and the vase will biodegrade. That's fine. So you don't have a waste. So it's good for the purpose. But just you have to think what is the life cycle of the product that is really going to happen, that is going to be used as a compost, or at least that we anyhow there is a chance that it will be composted. For the pan that we said the other time, for sure no one would ever compose that pan, right? In this case, yeah. Resource renewability. I should say a few things about this. Can you tell me one renewable resources in terms of material, let's say? Can you tell me one material that is renewable? We saw one here. You can say this or another one. cornstarch. Okay, but okay, and where you're seated on, it's a wood shell. So even wood or corn, it's a typical, to say that this is renewable. But even there, either is corn or is wood. With wood, it's more clear that this wine is taking you there. You can say that the same type of wood, for example, the one that is used for your chair, it could be renewable if it's coming from a plantation of Finland, where they are very careful in cutting only what regrows. But it could be the same type of wood, not renewable, if it's coming from another place where deforestation is what is usually made. The same type of wood. So it's not just a matter of the quality of the wood that has some characteristic, the speed by which it can regrow, but it depends even, yes, on the extraction frequency. So for example, this is made of plastic, so where is this coming from? Oil, right? So I'm drinking through a glass made out of oil, which is not that nice to think about it. But if this is the only product that the whole humanity is doing using oil, we could say that this is a renewable material. Okay, even oil has been produced during millennium and millennia because of the vegetation that was, all the process. So if this is the quantity that I'm using in relation to the speed, which is very slowly of regrowing of oil, this is compatible. I could say that this is a renewable material. Of course, this is not the reality, but just to make an example and to let you know what when we speak about renewability, we have to take this into consideration. So basically the definition is that we can say that the resource is renewable when the entropic, the humankind consumption rate is near the natural regrowing rate. It's lower than that. And about the environmental impact of material, I have even here to say something. Because okay, there are some quality related to the material. We can make a life cycle assessment of 1 kilogram of, let's say, a composite material, which is made of a plastic, a polymer, and then with some fiber inside, make it composite, resistant. Okay, I make a life cycle assessment per kilogram is that, and I may say this has an impact. As we said before, okay, global warming, maybe other things, and maybe the overall impact and so on. But then if I'm using that composite material for this glass that is going to be thrown away in a while, we could say that this is the worst, okay, material, because it's consuming lots of energy, it's very difficult to be recycled because it's made of mixed material and something like this. But if I'm using that composite material for the product we saw the other time, a motorbike, as one example, that material is making the motorbike to be lighter. So consuming, since it's lighter compared to other material, it makes the motorbike consume less resources and emit less per kilometer made. So in terms of the functional unit, it could be a very good material in terms of environmental impact. So again, here we have to be careful. What is the product? What is the life cycle of the product? What is the functional unit we are considering and so on. So I don't like so much to make a ranking from the worst to the best material. Of course, there are some. If I'm thinking about asbestos, this has to be phased out. And other, in principle, if they have high environmental impact, let's not consider them. But then it depends really when you go into the product you are considering to see what is the real characteristic and the real impact. And you can measure this with life cycle assessment if you want. Okay? Even this is important. Remember this because now we have, even though there are lots of several limits, but we have a tool that can tell us, really considering all the environmental impact, if a product or a concept that you are developing is better than another one. Okay? So it's not that we are anymore in a vague situation in which we really don't know what could be best or what could be a better solution than another. Product life optimization, it means to design for extending product lifespan, to design for durability, and to design for intensifying the product use or the use of the company, so that the product is more used in a more intensive way. So it could be that I'm using this computer, then it's used by machine in the office, and then so by other person. If this is used in a more intensive way, this has a lower environmental impact than I will see. One example of product life optimization is this. This is produced by Stockton. It's called Care. It's kids are growing. So in the first stage, this is a changing top. Then it can be reconfigured and it become a heat stable and then a writing desk. And designing this to be reconfigured, following the growth of our children, it means that we are using one product instead of three. So we are extending the life of this product. Believe me, there are lots of other things to be said, but here I have no time to speak about it. But just to give you an idea. But basically, why and where we reduce environmental impact if we extend the life of a product. This is an example up there of a product with a short lifespan. So pre-production, production, distribution, and use phase. Now you know why we speak about that. And then we have another one with the same function, but it lasts much longer in time. We have the function timeline over there. So where we avoid the impact? We avoid the impact because we don't have to dispose that product. We don't have to throw it away. Okay, the one that doesn't last longer. But we avoid even the impact of the product that's in relation to the functional unit, as we saw before, that need to be pre-produced, produced, and distributed. Okay, because if that was the chair, I need to sit here, and I need to have, if it's a covered seat, I need another covered seat, another covered seat, and so on. So actually, where we avoid the impact is there. It could happen for those products like, for example, a car or a computer that are using energy or other resources during the use, that new technology along the time may determine a reduced consumption during the use. So, for example, a new car is coming out with an engine that is working more efficient. And so what happens is that actually there we are changing the product, so we have an additional impact, but we have a lower impact in the use phase. So there you can make actually even a life cycle assessment to assess whether the advantage of reducing the impact in the use phase is more than the added impact, or actually you can design, and this is what we are suggesting, to substitute those parts that determine the energy consumption. For example, in a computer, maybe there is something that determine the consumption, and I can substitute that part, and by substituting only that part, the energy used will be similar to the other one. Okay, so I can design for disassembling and substituting simply that part. So I have an additional impact in the pre-production, production, distribution, and disposal, not of all the product, but simply of that part. But then I have a reduction in the use phase as before. And when intensifying the use of the product, why it is interesting? Because we can make an example of a drill. A drill is something that it's I have one at home, as some of you maybe, I don't know. But we are using, if you are not carpenter, we are using wall and wire. It's not that oftenly used, okay? So basically, we have the pre-production. This is a product that is intensively used. So let's say that it's used by Albert in time 1, time 2, and time 3. Then it's used by Beatrice in time 1, time 2, time 3, and then by me, Carlo, another time. So it's used in an intensive way. So someone is passing this trade from hand to hand. Okay. If we compare these to a situation in which we don't have an intensive use, there is Alberto, I don't remember the name that I invented before, that is using in the same time, but then we have another trade that is used by Beatrice the same time, and then this I remember by me in this other time. Of course, the additional impact are given by the fact that we have additional pre-production, production, distribution, and disposal of these other two rails compared to the preliminary situation. Of course, this is schematized situation, but to give you an idea. In fact, this is linked to when the lifespan is independent from the length of use. I don't go into the detail of that because it's a bit complex here. But you get the point, right? When we speak about material life extension, what does it mean? Design for recycling, design for energy recovery, and design for composting. And again, here I want to show you why we have an advantage when we design for recycling. Let's say that this is the upper case, and we show another one here below. Is a case in which we don't extend the life of the material. To extend the life, it means to give a new value to the material after the product has ended its lifetime. Okay, we design as long as possible, but then let's give a value instead of landfilling an environmental value to this product. So that is going to landfill, which is an impact. Or what we can do, we can recycle, we can incinerate with energy recovery through combustion, or we can put it throughout composting processes. And all those, the recycling, the material, or the energy, or the compost, it depends what is product we are using, it can enter another production cycle. Okay, so it can be used, you use a recycled material to produce another product. You use the energy for some processes during the production processes or during the use phase or so on. That means that for those we avoid the pre-production of comparable product. If I'm using a recycled material to make some part of this, I avoid the pre-production of virgin material, so it's coming, let's say, if it's a plastic polymer coming from oil, I have to extract the oil, refine the oil, and so on. So I avoid that process, the pre-production processes. I have some additional impact there because, in fact, the recycling is not without any impact. When I have to recycle, I have to collect the product, I have to transport it, I have to make some processes to make this to be reusable as a polymer for injection molding or other processes to make it, to be used for the same product. But basically, these processes are with a larger environmental impact compared to the fact. Think about when I have to make a polymer, I have to extract the oil, to transport it, to refine it, and compared to the fact that I can take it maybe to the waste, that if it's well collected and it's maybe differentiated, the collection of waste, it could be well made and so on. But this has to be taken into consideration as well. It has to be well designed. So in fact, even here, the recyclability of material depends on the specific characteristic of the material. It depends. I mean, for example, the metals are easier to be recycled in the sense that they recover the original characteristic of performance compared to the polymer. Polymer usually thermoplastic lose some properties because when they go throughout the thermal process, they lose, the polymer are made of chain of monomers, and when they go through a heating process, this chain get smaller and this, reduce the property the young. Several things. I'm not going to detail of that. Okay, so so it depends even on the characteristic of the material. That is easy to be said. But it depends even on the architecture of the system. Maybe I have a very good material to be recycled. I can take out all the, quality, the performance will be as the product at the beginning. Maybe it has even a good value. It's gold here inside. But then it's that difficult to be taken out of this product. That is a hell of a job because I have to take away its gloom with something that is so easy to be taken out that it's such an effort in economical and maybe even environmental terms to have that material that could be good in terms of own propriety to be recycled, that by the architecture of the same product, it won't fit because I have to make so you get things that I have to do something to design it in a proper way. But then it depends even on the recycling phases or the recycling system. As I said before, for example, if I have to transport to recycle some polymers, I have to transport these for kilometer and kilometer. A product that is, for example, a bottle of plastic, which is just a thin layer of plastic with lots of air inside. So I'm transporting very little quantity of plastic in a big truck, all right? And I'm transporting this for several kilometers, and maybe the oil that I'm saving because I don't have to produce any plastic is less than the oil that I'm using for the transportation. Right? And this happened some years ago when some rules, some legislation were made in Germany for the collection of plastic material. They were not here, so from Italy we were sending plastic material up to Germany and then taking them back here without really no sense, economical and environmental no sense. So it has to be understood even which is the recycling process. And in fact, when thinking about the recycling process, it's good to understand that even this is a cycle. And when designing, we have to design considering the fact that any material, this one, need to be collected. I will put it in the bin there, and then transported, separated, disassembled, and then identified it to know what kind of plastic is this. Because it's different one plastic from the other. If this is a polypropylene, I cannot recycle with a polymethyl methacrylate because the melting temperature is different, so one will burn while the other is not yet melted, and so on. So I have to know all these kind of things, okay? And the cleaning, because many times, over any product I may have some label or some other things that need to be cleaned and so on. And then I have to produce a secondary raw material. So while designing, we have to consider all these phases to design so that we can make all these phases with a low environmental impact. So design for recycling is not just to say I use a recyclable material. It doesn't say anything, okay? It's much more complex, and I would rather say even somehow more interesting. So here I have an example. This is a bottle of plastic, and this has a ribbon structure, spiral ribbon structure. They are using this to make it, there is an avian that is, yeah, okay, good. It's a bit different, it's the new model. But you can compare to another one, and you will see that this is being ribbed in this way that give rigidity to the plastic. So there is not so much plastic, and the ribbed makes it. In other cases, maybe you have a ribbed structure, but then to smash it could be quite difficult in other cases. In that case, since it's made on purpose to have it to be smashed easily, that's a design that think about the end of life and the transportation. Because if I transport a bottle of plastic, which is not air, if I'm not transporting air, but I'm transporting really plastic, it's better because we have to consider in terms of functional unit, which is the quantity of plastic that I'm transporting over a given track. If I can transport only 4, because they are not, if I'm transporting more air than plastic, it's quite different. So I have to divide by 4 in one case and maybe per 1,000 in another case, and so the impact is definitely different. And but here they made a mistake. I don't know if it's still there in that bottle. Can you tell me what is the mistake that they did in the design exercise here? The design of this bottle. What could make it a bit more difficult with recycling in relation to other cases? Maybe that is even paper based. And actually the fact that you can smash it down in that way, it makes it even more difficult to take this paper and the glue outside. So sometimes now they are saying smash it in this way and not in this way, because then it's easier to take this. But as I said, why not to make, if that is a polyethylene terephthalate, why not to make, you can do that, the label with the same material. So using a monomaterial strategy as it is said. Okay, here we don't have the time to speak about that, but just to give you an idea. Design for disassembly, this is functional to, as I said before, to product life cycle optimization and to material life extension. To product life optimization in terms of substituting some part. For example, if this computer is technologically obsolescent, so I have to change it after a while, not because it's not working anymore, but because it doesn't stand anymore, you know, the new app that I have to use, the new app, I have to throw away and buy a new one. But if I design for disassembly and, you know, so to substitute those parts that would enable, for example, to extend the memory, to enable my computer to perform for the new technology and the new app and so on, then I can extend the life. So in this case, it's the substitution of some part. And I think could be said. When we speak about material life extension, is the matter of designing for material disassembly. For example, for that bottle, if I make it so that while smashing it down, for some reason I designed the label that it will break because I made it in a certain way that it will simply be separated for some reason, or that I make it easy to be separated before doing that process, then but that is related to the material, those materials that are incompatible, so not related to components, but basically to component material. Okay, here cannot really go into any detail of that. You know, if you want, there is. I told you there is a book I wrote. There are another. That are really. There are a lot of knowledge to be aware of when you are designing product. I think it's quite important. And so, for example, Herman Miller is well aware and competent about that. So they are designing for disassembly, both for recycling and for component reuse and so on. So in fact, yeah, maybe you remember they are usually giving their chair seats with a 12-year warranty because they are designing those to last very long and to substitute some part if something has happened. And then for your knowledge, several methods has been developed, and even this maybe I told you the other time. There is one that is the method we are using. It's an Italian book. The other one that I may suggest, if someone wants to go to see, this is a booklet from United Nations Environmental Program on design for sustainability, a step-by-step approach. There inside there are some tools you can use and some suggestions. Well, actually now I made a contract with Springer to republish that book in Italian. It will be available in a while, but this is, I think you can download it for free if you are interested. I wrote even into that book, but related to PSS, not to product design. So other colleagues from other parts of the world wrote. And there are some good. So if you want to look at a tool, maybe that's a good book to look for. So this is, I go fast over here, is just to say that what we develop is a design methodology that support the normal design processes. It's made in a modular way so that you can use different tools in different ways. And these are some tools that we develop, and some of those are in English that you can download from the platform. They are easy to use too. They are in Excel form as far as now, so it's very usable. And since they are in copyleft, so Creative Commons license, people can easily change if they want to readapt, translate to other languages. It's not, a very complex software that is made. Okay, and so if anyone is interested even in other languages, my book, maybe I told you the other time, I translated in few languages, in Portuguese, in English, in Chinese, and in Spanish, of course. In Italian,